Hi, I'm Georgia Kiko,
And I'm Alexa Langenfeld.
and we decided to do our material selection project on a soccer ball. Here's our table of contents, including our equations and values, free body diagrams, and all of our performance and cost graphs. Here's our design requirements table for the soccer ball. For the function, the ball is to be used for soccer and able to withstand outdoor weather conditions, the force of a kick, and it's also able to retain its initial shape. The constraints for this project are the specified density, spherical diameter, and the water resistivity. The objectives for this project are the high performance of 100 parts, the low cost with 100,000 plus parts, and overall we want to minimize the cost and maximize the toughness. The free variables are the choice of color and the choice of material. Here are our equations and values for the project. Since the soccer ball is a pressure vessel with air on the inside, we decided to use the inner and outer radii to find the volume and then use that value to find the density of the ball. We also assumed that the inner bladder of the soccer ball is a butyl rubber bladder and also calculated the density of the entire ball and the density of the ball without the bladder on the inside. We also calculated the maximum force from the kick. We want to maximize the toughness and minimize the stress. We also included some photos of a pressure vessel for the Young's modulus equations. We also made a note that our important critical mechanical load conditions are that the material must withstand the specific internal and external pressures and that the stress is evenly distributed across the surface.
This slide has our free body diagrams for our soccer ball. On the left it has the forces that are external, and on the right are the forces that are internal due to the pressure vessel. The worst case scenario is impact and strength of tension or flexure from bouncing, rolling, and the kicking force of the ball. This slide shows our graph where we chose our material. We based it off cost per unit of strength versus toughness, and we added limitations to density, fresh water, and UV radiation. So we chose the best material for low cost would be expanded PS foam, and the best material based on performance would be polyurethane foam. These were the materials that showed up on our graph. So the top two materials you will see highlighted as expanded PS foam and polyurethane foam. We compared the density, water durability, UV radiation, toughness, cost, and then included some examples of what they typically are used for. So the expanded PS foam was the least expensive, and then the polyurethane foam was more expensive but had the best performance. In summary, for low cost, we chose expanded PS foam because it was the least expensive material that was within our constraints for a soccer ball. For best performance material, we chose polyurethane foam because it had a higher toughness and would be able to withstand adverse conditions.
This slide shows the performance and cost of our two chosen materials from the previous slide. In the graphs, it is economic batch size in units versus relative cost index per unit in US dollars. As is seen, the polyurethane foam, the only process that works with this material is the rotational molding, and it only works up to 10,000 units. And for the expanded PS foam, thermoforming is the best process chosen, and it only works up to 1,000 units. For our additional design element, we decided to do a hybrid design. We wanted to include a multi-layer laminate on the outer cover to keep our inner layers dry and to increase the resistivity to outdoor environments. Some of the constraints we used for this graph were that we wanted it to be a thermoplastic elastomer, that the resistivity to water was excellent, the UV radiation resistivity was excellent, and that it had to be a painting and printing process. Based on the results from the chart, to maximize performance, we decided that the TPU was the best option. TPU coating is fully degradable and also has excellent durability. To minimize cost, we would use the POE or POP as a coating.
For manufacturing and cost analysis, polyurethane foam uses rotational molding because it is the best option for high performance and creates a batch size of 100. Expanded PS foam uses thermoforming as the best option for the least expensive material. Cost per part, for the least expensive soccer ball, we used expanded PS foam as the outer layer and POE/POP as the coating. The least expensive cost of the materials would be $2.07. For best performance soccer ball, we used polyurethane foam as the outer layer and TPU as the coating, and the cost of the more expensive soccer ball would be $4.22. In summary, as we found throughout this project, the best materials are not always the least expensive, but the more expensive ones will be more durable and last longer. We chose expanded PS foam as the cheapest material, as we found in our graph, but it is unable to mass produce the batch size of 100,000. We also tested PVC cross-linked foam and phenolic foam, but both of those had manufacturing techniques of thermoforming as well and were more expensive than the expanded PS foam. Additional research shows that nearly 70% of the world's soccer balls are made in Pakistan, and in this factory they are largely still made by hand. Therefore, it makes more sense that our analysis shows an inability to make batch sizes of 100,000 plus with the optimum materials. Expanded PS foam is the least expensive, but due to its manufacturing process, it cannot produce as large of a batch size. Meanwhile, polyurethane foam is the optimal material for performance and has a manufacturing process that produces the larger batch size. Thanks for listening, and here are our sources.